Algebra 2, Section 2.6, Find Rational Zeros. So, what are zeros? Well, zeros are the solutions of a polynomial and the x-intercepts of its graph. So if I have a polynomial, the graph's something like this. It would have 3 zeros, one here, one here, one here. They're called zeros because that is where y equals 0. Think about any point on the x-axis has a y-coordinate of 0. So, how do we find zeros? Well, a good place to start is with the rational zero theorem. This is a way to find all the possible rational zeros or solutions of a polynomial. Now remember, rational numbers are numbers that can be written as fractions. They will not include things like square roots unless it's a whole number. They will also not include imaginary numbers. Now, this rational zero test will give us all the possible rational zeros or solutions to a polynomial. What this test says is that we take p over q, which p just stands for the factors of the constant term of the polynomial. Now, the constant term is the one that does not have an x with it. Makes it constant. Then we divide all those factors by the factors of the leading coefficient. And remember, the leading coefficient is the number that's in front of the highest power of x. This will give, once again, all the possible rational zeros of a function. Let's see what that looks like. So, to find all the possible rational zeros for this function, I want to first look at the constant term. Here our constant term is 1. Well, factors of 1 are just positive 1 and negative 1. Now we would need to include the negatives as well because a negative 1 times negative 1 still will equal a positive 1. So I'll write that on top as p, positive negative 1, divided by the factors of the leading coefficient. Look for the number in front of the highest exponent. And we want factors then of 2 to be on the denominator. Well, what things go into 2? 1 and 2. And once again, we need to consider both the positive and the negative. Now, let's go ahead and see what numbers that gives us. 1 divided by 1 is just 1. So we have both positive and negative 1. And then we have 1 divided by 2, which would be positive negative 2. So here we have 4 possible rational zeros. Now, that does not mean that all 4 will actually be zeros. These are just 4 possible rational zeros. Also, these only include the rational zeros, not the irrational or imaginary possibilities. Let's try another one. For this function, I want to put the factors of 6 on the numerator. That's our constant term. So I need to list all of them. So 1, 2, 3, and 6. All are factors of 6 divided by factors of the leading coefficient. Well, here the leading coefficient would just be 1 because we would have 1x to the 4th. So I'll put that over positive negative 1. So dividing each of those by 1, well, I just get these 8 possibilities: positive negative 1, positive negative 2, positive negative 3, and positive negative 6. So here I have 8 different possible rational zeros. Let's do another example, and we'll also look at why this works. All right, larger numbers mean we have more factors. So, looking at our constant term, a lot of things go into 16. Positive negative 1, positive negative 2, 3 does not go evenly into 16, 4 does, 4 times 4 is 16, 5 does not, 6 does not, 7 does not, but 8 does. 8 times 2 is 16. And then let's not forget 16 either. Then divide that by the factors of the leading coefficient, being 2 here. So we'd have positive negative 1 and positive negative 2. Now, we need to divide all those out. Well, each of those divided by 1 is just all of those listed again. So positive negative 8, 16. Then I need to go through and divide each of my numbers by 2. 1 divided by 2 gives me positive negative 1/2. Let's see, 2 divided by 2 equals 1, and I already have that listed. 4 divided by 2 is 2, I already have that listed. 8 divided by 2 is 4, I already have that listed. 16 divided by 2 is 8, so I have that listed as well. So it looks like we have 2, 4, 6, 8, 10, 12. 12 different possible rational zeros. Now, let's think about why this works. If I were to solve this equation by factoring, well, I'd look and I see I have 4 terms, so I could factor by grouping. Now, solving it by factoring is another way to find the zeros of the function. Zeros are just the solutions. What makes the function equal 0? So, if we set this equal to 0, and since I have 4 terms, let's factor it by grouping. Group the first 2 terms together, plus sign. Group the second 2 terms together. Make sure you get that negative in with the 32. And then I'm going to look at each group. From the first group, I could factor out an x squared. And then I'd have a 2x minus 1. From the second group, I could factor out a negative 16, leaving me with 2x minus 1. And it does look like this will work to factor by grouping since I have a common binomial factor of 2x minus 1. So let's factor that out in front, 2x minus 1. And then I'd be left with the x squared minus 16. And I can factor this yet further. 2x minus 1, I can't factor that further, but then I have the difference of perfect squares here. So I'll factor into x plus 4 times x minus 4. And then remember to find the solutions or the zeros. Since the product of these equals 0, I can just set each of those factors equal to 0 and solve. So with this one, if I set equal to 0, I would add 1, divide by 2, and I get x equals 1/2. For the next one, I'd subtract 4, and I get x equals negative 4. And for the third one, I'd add 4, I get x equals 4. So you can see I ended up with 4 rational zeros. Now, look back at your list. When we listed all of our options, remember in our list we had both positive and negative 4, and I had both positive and negative 1/2. Well, notice those line up with my actual zeros or solutions. Think about where these numbers come from. If I multiply first times first times first, as I multiply this out, I would get 2x times x times x, and I would get 2x cubed, my first term up here. Last times last times last would give me positive 16, which matches with what I have here. So when we do the rational zero test, the whole p over q, notice what goes on top. Factors of our constant term. Well, those factors end up being represented here, here, and here. So when I solve for x, that's what I moved over to the right side first. Those became the numerator of the 0. Then the whole the q on the bottom, remember that comes from factors of our constant term. Notice here, the 2, the 1, and the 1 would be factors of our constant term, and that's what I end up dividing by when I solve. So when I added 1 and divided by 2, I divided by a factor of the constant term. And that is why doing this, p over q, will contain all the possible rational zeros. Now, we had a big list of possible rational zeros, and notice we ended up with 3 that are actual zeros. Now, we aren't always going to be able to factor to solve these actual zeros, so let's look at how else we could find them. So a number n is a zero or a solution of the function if f of n equals 0. So if I plug in n into the function and I get a result of 0, well then I know it's a 0 of the function. So To find the actual rational zeros from the list of possible rational zeros, we are going to plug the possible zeros into the function to find the actual zeros. You can use either direct substitution, where we just plug it directly in, see if it equals 0, or we can use synthetic substitution. Now, direct substitution is probably a little bit faster, but synthetic substitution will help us find other non-rational zeros. So I will usually do the synthetic substitution for that reason. Let's revisit our first example, but now go back to find the actual rational zeros. Remember before, we found 4 different possible rational zeros. Positive -1/2, positive -1. What we can do is plug them each in for x one at a time to see which of those 4 get a result of 0. So if we start out with plugging in -1, or let's start with -1/2. Now I plug that in everywhere I have an x. So 2 parentheses -1/2, raise that to the 3rd power, plus parentheses -1/2 squared plus 2 times -1/2 plus 1. Now, when you plug this in your calculator, it's going to be important to get parentheses around whatever number you're plugging in if it is negative. If it's positive, it shouldn't make a difference, but if it's negative, we do know that a negative squared equals a positive number, so our calculator needs to know that we are squaring that entire negative. The exponent should go on the outside, the -1/2 on the inside of the parentheses. Now, to save yourself some time as you do this, you can either use a calculator where you can pull back up what you entered in before, and then I could go through and take out the negatives to plug in 1/2. Then I could pull it back up, delete the 2 and the fraction, leave it as 1 or -1, and I could plug those in. Another fast way to plug in these numbers would be using the table feature on a graphing calculator. What you could do is underneath y equals, put in the function. So that is y1. And then on the table, set the table so that it will ask you for the input, but tell you the output. Then as you plug in each value, you can just look at the table to get the results. So go ahead and try this on your calculator. Try -1/2. And make sure that you get 0. So there we found our first 0 of our function. -1/2 is a 0 because f of -1/2 equals 0. Go ahead and try 1/2. When you plug that in, you should get 2.5. So it's not a 0 of the function. Go ahead and plug in -1. Pause if you need to. And you should get -2. Now plug in 1. When I plug in 1, I get 6. Is that what you got? So we can see that -1/2 is the only rational zero or solution. The rest will either be irrational, like the square root of 3, or imaginary numbers I, involving I. And we'll look at those and how to find those a little bit later. And we'll also, in this case, notice I did go ahead and just use direct substitution as I plug these in directly. When it comes to finding the other solutions, that's really when synthetic substitution is going to make things a lot easier. Now let's revisit example 2. In example 2, we found, for this function, we found 8 different possible rational zeros listed here. So let's go through, plug them in. Let's see which ones will give us a result of 0. Now, if I'm using a calculator where I'm pulling back up what I put in before, it's going to be easiest to first go through and plug in the negatives, because then you already have the negative in there. You can just change the second part of the number. And then I would go back, delete the negative, and insert the positive numbers. And I can do that without then having to reinsert negatives and positives that I go back and forth. So you plug in -1, you should get 0. So there's our first 0 for this function. Plug in -2, you should get 4. Plug in -3, you should get 60. Plug in -6, you should get 1,320. So no more zeros for our negatives. Then go back, plug in 1, get 4. Plug in 2, I get 0, so there's another 0. Plug in 3, I get 24. And plug in 6, I get 924. Make sure you're getting those same values on your calculator. So we can see I have 2 actual rational zeros. My actual rational zeros are -1 and +2. Now let's look at how to find all the real zeros of a function. Well, if you're asked to find all the possible rational zeros, all you have to do is the P over Q and list out all those positive, negative options. If it asks you to find all the actual rational zeros, then we have to plug in each of those and find which ones equal 0. Now, if it says find all the real zeros, well, zeros include not only rational numbers that we can find using the rational zero test, but it also will include irrational and imaginary solutions. And it's asking us to find all of them. So I am going to start with the rational zeros, and particularly the possible rational zeros. So again, if I look at the constant term, I can list out all of its factors on the numerator. So 1, 2, a lot for 12, 3, 4, 6, and 12. Make sure you include the positive and the negative. Divide by the factors of the leading coefficient. So factors of 9, positive -1, positive -3, positive -9. So we have a lot of options here. As I go through and list them, each of them divide by 1. So I have positive -1, 2, 3, 4, 6, and 12. Then I'll go through and divide them each by 3. So that will give me 1/3, 2/3, 3/3 is 1. I already have that listed. Then I have 4/3. 6/3 is 2. I already have it listed. 12/3 is 4. I have that listed as well. So now I need to go through and divide by 9. And I have then positive -1/9, positive -2/9. 3/9 would reduce to 1/3. I have that listed. Then positive -4/9. Positive -6/9 would reduce to 2/3. I have that listed. And then positive -12/9 would reduce to 4/3. I have that listed as well. So you can see we have a lot of possible rational zeros here. Now, I'm not necessarily going to go through and plug them all in. What I want to do is find 1 or 2 of them and then use synthetic division to divide out my polynomial. So let's start by plugging in 1. Go ahead, plug in 1 for x. See what you get. When I plug in 1, I get 0. All right, found our first 0. Let's plug in a couple more, see if we can find another one. Then I'll show you what we'll do with those. Plug in -1. All right, when I plug in -1, I get -18. So that's not one of our actual zeros. Let's do positive -2 next. When I plug in positive 2, I get 72. So that's not a 0. Let's try -2. Now again, I might prefer to go through and do all my negatives first and my positives. Plug in -2 and I get another 0. All right, so far we found 2 actual rational zeros. Now a hint here, if my degree is 4th degree, that means I will actually have 4 zeros. Now, could be a combination of rational and irrational and imaginary and repeated solutions. We'll look at that more tomorrow or on the next lesson with the fundamental theorem. The fundamental theorem of algebra will tie all of this together. All right, so far I found that 1 and -2 are actual rational zeros for our function. So what I want to do now is use synthetic division to narrow down my polynomial. Essentially, I'm going to divide out those factors. A 0 of 1 would go with the factor of x minus 1. Because remember, if we got this factor, we'd set equal to 0, add 1 to both sides, and we get 1 as a 0. -2 goes with the factor of x plus 2. Because if I got a factor of x plus 2, set equal to 0, subtract 2 from both sides, and I get an answer solution of -2. So I'm dividing this polynomial by the factors using synthetic division. And remember, it's a process of add, multiply by the 1, add, multiply, and I get a remainder of 0. So good sign, it should be 0 there. And now what I'm going to do, so that was my first 0, and this would bring me down to a polynomial of 9x cubed plus 3x squared minus 18x minus 12. So now I'm going to take -2 into that resulting polynomial. So let's set -2 up here. I'm just going to continue the problem. Now I'm not going to use the remainder here. I'm just going to take -2 into the remaining polynomial. And again, bring down the first number, multiply, add, etc., multiply, add, multiply, add. And again, another good sign, I have 0 as my remainder, so that confirms that -2 is a 0. And now let's look at our resulting polynomial. Our resulting polynomial is 9x cubed. Whoops, not cubed, it'd be actually 9x squared. Because I divided it twice, this brought it down to 9x cubed. Now we're down to 9x squared minus 6x minus 6. Now, once I get down to a quadratic equation, I could try to factor it from here, but if my other zeros are not rational, it's not going to be factorable at this point. And I could have kept plugging in all my other possible rational zeros for this, but really once I find 2, it's really going to slow me down to keep going, because what I want to do now is to find my other zeros by solving this quadratic formula. Well, if it's not factorable, how else can I solve it? Well, remember, quadratic formula. So let's plug it in, see what we get. X equals opposite b, plus or minus square root. B squared, which would be 36, minus 4 times a, which is 9, times c, which is -6. And that's all over 2a. 2 times 9 would be 18. All right, so let's simplify this. So we get 6 plus or minus the square root of 252. I simplify what's under the square root, divide by 18. Sometimes it's going to be good to simplify this in parts, just in case we have an imaginary number. Now let's simplify it further if we can. The square root of 252. Well, 252 square root is not a whole number. However, I could split the square root of 252 into 36 times 7. And I want to kind of try any perfect squares that go into it until I find one that works. 36 goes evenly into 252 7 times. And the square root of 36 is just 6. So what that allows me to do is to rewrite the square root of 252 as 6 times the square root of 7. That's still all over 18. Now I can simplify a little bit more since all of these are divisible by 6. Think of reducing these as fractions. 6/18 would reduce to 1/3. And 6/18 again would reduce to 1/3, so I could write that as square root of 7 over 3. Running out of space here. So let me get some space cleared up and I'll rewrite this. All right, that's better. So coming up here with this, I had 1/3 plus or minus the square root of 7 over 3. So notice that gives me 2 more zeros, and those are irrational zeros because the square root of 7 is irrational. 2 solutions because of the plus minus, plus another 2 solutions up here, and notice I have 4 real zeros for this function. Notice also, it's 4th degree. Let's apply this knowledge to a word problem. A prism has a square base with a height that is 5 feet longer than each side of the base. All right, let's sketch what that means. So a prism has the same shape all the way up, and we're told that that base is a square. So if I look at the base, all right, and I know it's a square, so let's label it x by x. Then we're told that the height, so here's the height of the prism, is 5 feet longer than each side of the base. So we can represent that with 5 plus x. The volume of the prism is 28 cubic feet. What is the height of the prism? Well, I could do a whole guess and check strategy, knowing that the volume is length times width times height. And I could start out by plugging in, say, 1 for x, see if it equals 28. If it's too small, increase x till I get the right option. But let's go ahead and apply what we've been learning. Let's plug in what we know to our equation. Volume is 28. The length is x. The width is x. And the height is 5 plus x. So notice I'm going to have a polynomial here. X times x is x squared. I can distribute that to the 5 plus x. So I get 5x squared plus x cubed equals 28. Then I'm going to set it equal to 0. I'm also going to put it in standard form, so I'm going to put the x cubed first, then the 5x squared, and then the 28. Now to solve this, I want to find the zeros of the function. And if I start with looking at the possible rational zeros, so we can look at p over q. So I can at least use the rational zero test to narrow down my options. All right, the constant term is 28, so I have quite a few options there with 1, 2, let's see, 3 is not a factor, but 4 is, 5 is not, 6 is not, 7 times 4 is 28, 14, and then 28. Then divided by factors of leading coefficient, well, we just have 1x cubed, so just positive -1. Now, because I'm dealing with length here, I know that x, the length, cannot be negative. So I don't even need to test -1, -2, or -4. I also know that it's not going to be something too large like 28 because, well, the volume's 28. And if I have 28 times 28 times 28 plus 5, well, that's way beyond a volume of 28 cubic feet. So I'd start with something smaller. Let's start with 1. If I plug 1 in here, I'd have 1 times 6 would give me a volume of 6 that's too small. Let's try 2. 2 times 2 times 7, and I got the 7 by taking the 5 plus the 2 here, and that's 4 times 2, which is 28. So it looks like x being 2 feet would give me a volume of 28 cubic feet. Now let's come back to what the problem's asking. It's asking for what is the height of the prism? Well, the base is 2 feet by 2 feet. The height is 5 feet more than that, so we're looking at the height of 7 feet. So notice I used a combination there of the rational zero test and a little bit of guess and check to plug in what worked. So the rational zero test could save me a little bit of time. Now, this problem did work out nicely as far as having a nice whole number for x. It gets a little trickier if I have fractions or irrational numbers for my values. That concludes this section, 2.6, Find Rational Zeros. Thank you.